Hi, thank you for having me here. I'm Itamar, and I'm here to keep you from going to lunch on time. My talk is about boring use cases for exciting types, and a few words about me. I'm a freelance software developer based in Israel. I've been doing functional programming mostly in Scala for the last couple of years. I specialize in helping companies break down monoliths and move them to more microservices-based architectures, and do some DevOps along the way. I also co-organize the _Scala meetup in Israel, so if you're around town, give me a call. And hit me up if you'd like to work together afterwards. Now, my Twitter handle is at the bottom of the slides, so tweet at me if you'd like. And let's talk about why I wrote this talk before we get on to the boring use cases. And functional programming is really great. Right? Life is really good when doing functional programming. We can produce reliable software, 0 bugs, and we can onboard teammates really quickly, right? Well, not quite, because even though functional programming is just about programming with functions, nothing could be simpler than that, and types, of course. And these functions that we're programming with, they have 3 very useful properties: that they're total, deterministic, and pure. And as John says, everything else is just composition that you can learn over time, right? You can tell that to your teammates. Don't worry about these exotic type signatures that you're seeing. So the question here is, how exactly do we execute that last sentence? Or in other words, how do we grow as functional programmers? Let's take a particular use case for this. Here's a poster child for functional programming. It's a quicksort in Haskell. It's very declarative. It's very straightforward, you could say, if you can parse the symbols. So a quicksort for the empty list is just an empty list. And the quicksort for a non-empty list is a quicksort of everything lesser than the pivot and everything greater than the pivot concatenated together. That's great. But how do we go from this to this scary construct taken from Edward Kemet's recursion schemes library? This is a post-promorphism. It's a recursion scheme that I am absolutely sure does something very useful, but I cannot tell what it does just by looking at it. Now, I've done the work for you, and what this does is that it can apply a sort of post-filter to a thing that you can unfold using an anamorphism, which is a generalized unfold. But the actual problem here is that we are lacking in examples in the functional programming community. Whenever I like to teach something to one of my teammates, I am sorely lacking in examples, or at least examples in articles I can point them towards. So this talk will be about giving you a few examples of purely functional type-safe time measurement and instrumentation, state machines, and resource allocation and release. So let's go. Let's get started. The examples ahead assume that you have the partial unification option, the Scala C, and the better monadic for compiler plugin, and these imports for cats in place. All right. So the first problem, which would be more of a warm-up than a very exciting data type, would be this. I have a bunch of computations right here. I have a function that computes the coefficient of variance for a bunch of data. This function is composed of several smaller functions, and I'd like to measure the execution time of each of these. OK. I'm pretty sure most of us have had to emit metrics or some sort of time measurements in our applications at some point, which is why this is a pretty boring use case. So our first non-solution would be to manually instrument everything, right? We could insert a timing call between each step in the for comprehension. And this is not very fun. I wouldn't like to maintain this sort of code base, right? I've had the pleasure of encountering these sort of patterns, and this is not very maintainable. So what we could do instead, or what we'd like to do, is have some sort of structure that allows us to keep the timing logged on the side while still focusing on the main data flow. And when we finish the compute CV function, we'd like to end up with the original double, the value that we were interested in, and the timing data on the side. So to start building this out, we can define a timed combinator. So what this does is it takes a I/O program that emits an A, the FA, and it decorates it with timing calls. So we get back an I/O program that emits a finite duration and an A. And this is only possible because FA is pure. This is just a value describing a program that when run will emit an A. So we can just pass it around. It's a value. There's nothing wrong with that. This is not a future that is already running. So we can also name this computation. We can also give it a name and return a tuple of a string and a finite duration along with the A. And now we can use our new timed function to time each step of the computation. But this is pretty tedious because we still have to keep track of each duration of each smaller function. And we need to, I don't know, render them, and it's not very fun. This is an improvement, but not so much. So what we can do to save us from that bookkeeping is use writer T. So writer T is a new type, or if we had new types in Scala, it would be a new type, around a tuple of a log and a value wrapped inside some type constructor f. And to be honest, this really is nothing more than a tuple. But tuples are pretty magical. So let's say we have some sort of metadata, a list of strings, and a type called annotated of A, which is just an A annotated with a metadata. And given this sort of person, if we have an annotated person, we can apply a function to the person using map, because tuples have a functor instance. And we can also even traverse tuples by applying an effectful function to the right-hand side of the tuple and pushing the annotation inside the effect. And if we have a semigroup for the metadata, we can even flat map computations that return tuples. So in this case, if we have an annotated person, we can extract the person from the annotated person, and then we can extract another person from another annotated person, and we can yield a new person. And this entire computation's type will still be an annotated person because we are yielding a person. And the value here would actually be a concatenation. The value of the metadata would be a concatenation of the logs in each step of the computation. So back to writer T, this is identical, except we have the underlying effect. And the type of our time program is this. It's a time program of I/O of a tuple of string and finite duration and an A. And if we adapt this to writer T, this will be a writer T of I/O, the tuple, and the A. Now, this won't sensibly work because, sorry, if you'd like to concatenate two tuples together, the two elements, the two components will be concatenated pointwise. So this is not exactly what we're looking for, so let's just use a map instead. We'll define timed of A to be writer T of I/O, a map of timings, and an A. And now we can define the time combinator to just return that type. We have the same function body, and we just wrap it with the writer T to get back a timed of A. Now, our original program is only slightly changed. Basically, the only thing that changed here is that we no longer have to keep track of the timing. Or in other words, we've made the timing ambient. We pushed it to the background, and it's being kept track of for us. And if you're into infix syntax, you can also do this with the implicit classes to make this a bit more, I don't know, easy on the eyes. We Scala programmers, we like infix syntax. And to unpack the timing data, we can also define another function that will kind of run the program, extract the timing data, print the timing data, and using some sort of effectful function or a logging algebra, and then return the original program, just as an IO of A. Which is nice because we can now use this to maintain the same interface for our compute CV function and still get the timing data printed out for us or logged to whatever you'd like. And this is very cool because we've used a very simple and not so exotic, but a lesser known data type, such as write-at, to implement a very boring use case. So this is a good example of making auxiliary details, such as timing ambient. And you can do many, many things with write-at. You can accumulate events if you're performing some sort of computation that needs to do event sourcing. So you can accumulate events that you'd like to emit at the end of the computation. And you can even accumulate errors if you're doing some sort of a computation that needs to emit partial results and errors. That's also possible with write-at, and many, many more things. So let's move on to the next use case, safe state machines. So my problem here is that I'd like to safely model an authentication protocol. So here's my authentication model. We have a case class representing our connection with a socket inside it. And the protocol is represented by 4 steps that need to be executed in order. We have a connection, a handshake, a credentials step, and authentication. And for example, the handshake function will execute some I/O programs, which will write data to the socket and read back from it and verify the resulting data. OK, great. So how do I use this? Well, I can just use the functions, right? If I have an instance of authentication in scope. So if I have the API, I can import all the functions out of it. And I can sequence them using 4 comprehensions because I'm working with the I/O monad. So this is great, apart from the fact that there is a bug in here. That was, I guess, pretty hard to catch. Because we have called the authentication function before we even sent the credentials on the wire. So the problem here is that nothing is actually keeping track of the proper call order, and nothing is preventing us from doing these sort of errors. So when in doubt, always add more types. So what I'm going to do is add a type parameter to connection called S, which will represent the next state that the connection expects to be in. So we'll also add some case classes, and I'm using case classes and non-case objects just to avoid some ugliness in Scala. We'll use case classes to represent the connection states. And now, what I can do is modify my API to take a connection of the expected state and return a I/O of connection with the next state. So for example, handshake will only be performed on a connection that expects to be in the handshake state, and will return a connection that has transitioned to the credential state. And making this work with the functions is not very problematic. For example, here, because the type parameter S in connection has no value representation, we can just copy the connection and get back a new value of connection with the right type parameter. So this is OK. But now, when we actually like to use it, we need to keep track of much more things. Because we need to keep track of this connection and handshake, and this connection of credentials. And in essence, it's all the same value. But we have to keep track of them ourselves to pass them to the right functions, which is not nice. It's safe, but it's ugly. So what we can do instead is use indexed state T. And indexed state T is another interesting data type from functional programming that is a new type around a function that takes an input state of start, right? Input state of start, and returns inside a type constructor F an output state of end and a result. OK, that seems pretty innocent. Now, if we set these for example, start to be connection of handshake, end to be connection of credential, f to be IO, and result to be unit, then we get back something that is very much the same as our handshake function. Okay, that's nice. And we can even name these sort of protocol transitions with a type alias, protocol A to B, which means a protocol transition from connection state of A to connection state of B. And our nicer handshake function now looks kind of like this. This is much more elegant. And we're saying this function is a protocol transition from handshake to credentials. Cool. So now, if we modify our API to use this, then our interface is much cleaner, I would say, because each function returns a protocol transition. And to actually use the index state t type constructor, then we only had to add this modify f method around the function body, which is to say that this is a function that only modifies the state and has no result. This is what modify f for index state t means. Okay, so this is how our usage now looks like. We have, again, made all the unnecessary details disappear. We pushed the state tracking to the background, and we've made it ambient, because now all the connections are being passed along between the functions for us. And the original example, so you see here that I switched the authentication credentials again. The original example now errors out with this slightly frightening error message, which is the only downside of this type. This is the error message that we'd get that we'd have to slightly parse to understand what we've done wrong, but at least it points us to the right line. The compiler now tracks for us the fact that we've done the state transitions properly according to the types that we've defined. So to summarize, index state t is very cool for type-safe transitions, and it is we've sort of glossed over it because we've used it in for comprehensions, but it is a monad and an applicative when the input type is equal to the output type. We can still use index states with different types in for comprehensions because Scala only relies on the presence of the flat map function. It doesn't care about its shape. But it is a monad and an applicative when SA equals SB, and then you get the plain vanilla state T. And for nonlinear transitions, if you need to keep track of, for example, multiple state machines, you could use shapeless scroll product into HLists. I'm not sure I would entirely recommend going with that, as that can be a bit convoluted, but it is possible. And if you're using Haskell, then this is available in the indexed extras package, again by Edward Kemet. And I've also seen that Oscar Wickstrom has a very cool package called Motor for tracking type-safe state machines using type-level lists. OK, that's it for protocols. Let's move on to resource allocation and release. So the problem here, and this is my favorite example from the last year, the problem here is that I have many resources located in my app, and I'd like to manage their allocation and release. So for example, here are two resources that I allocated in my app, a Kafka consumer and a database connection. Both of them can be gracefully closed using the close method on their type. Now, the only thing here is that I need to make sure that I close the resources in reverse order of acquisition. So this might not be very apparent here, but I'd like to make sure that the database connection is closed and all the pending writes are flushed before I close the Kafka consumer. Now, this could work, but there are two things that bother me here. So first, I have to keep track of the ordering myself. If I switch these two lines together, or I add more resources, then I have to make sure that I close them out in the right order. This is not very refactoring friendly. And the second thing here is that if something fails along the way, then I'm kind of screwed because, whoops, sorry. If something fails along the way, then I'm kind of screwed because if the connection closing for some reason fails, then I will not be closing my Kafka consumer, and I will be leaving phantom consumers on my brokers, and that's not good. So I can ignore the failures or something like that, but that doesn't scale. This is very, very smelly. This is code smell, right? This is just screaming for a better abstraction. So let's see what other alternatives are around. So if you know Java, you're probably aware of try with resources. Try with resources will allocate a resource defined in the try parameter list. And if it inherits from autoclosable, then when we exit that try block, there is an implicit finally clause added that we'll call the close method. That's not bad. Apart from the fact that it uses side effects and exceptions, that's not bad. The problem here is that our example would kind of look something like this. If I need another resource, I need to nest them. And well, this kind of reminds me of this Hadouken diagram. And I've actually gone to these sort of lengths before discovering the abstraction we're going to see. But essentially, this can compose. I mean, we can compose resources using this abstraction, but it's not optimal. What else? IO monads. They offer us the bracket operation. So the bracket operation on IO monads takes a program that acquires a resource, a program that will emit a resource of type R, a program that will release the resource, a function that returns an IO of unit given in R, and a program that uses the resource. So what this will do, the IO bracket operation, it will run the acquire, give the resource to the use function, and run the release function. And the guarantee is that the release function, much like the finally clause in the try, will run regardless of what happens in the use function. Okay, this is good. This is at least pure. But this kind of gets us to the same place. So here's the first acquisition, the acquisition of the Kafka consumer. And if we add the database connection, you can see that we're slowly getting to the same place. OK, I think we're stuck. And we'll need to take a leap of faith because in Scala Z, there's an interesting data type called codensity. Codensity, apart from its scary name and its category theoretic references, I mean, what is density, if this is codensity? Codensity is a highly abstract data type that is going to be very useful for our situation. So what this does is that it has an apply function that takes a function given an A, returns an f of b, and then returns an f of b. So if we set f to be IO, a to be R, and b to be A, apply looks like this. And this function right here is suspiciously similar to part of bracket, right? So the apply function from codensity here is exactly the same as this little part of the bracket operation. And remember, type signatures are never a coincidence, especially when you're working with purely functional programming. So what we can do here is that we can write a combinator for resources using codensity. So what we'll do is that we will partially apply the bracket operation. We'll take the acquire and release functions, and we will capture them in the closure of the produced codensity function. So we're producing a codensity, we'll call it resource, a resource value that when its apply function is run, it will execute the bracketing operation. OK, nice. So now, when we write resource, we get back a value. We get back a cadensity value representing our Kafka consumer. And now, we can actually use it. So when we write this, this is actually a bracketing operation, because we're executing the apply function on the codensity, which was set to be an io.bracket. OK, this is nice, but now the really fun part is that we are about to do composition of resources using codensity. So it just so happens, well, it doesn't so happen. It just so happens that codensity is a monad. So it has a flat map function, and I can write codensity values on the right-hand side of 4 comprehensions. So I can sequence computations that return codensity values using 4 comprehensions. But what is actually happening here? So let's look at codensity's flat map, and this is a difficult slide, so bear with me. Let's say that we have a codensity of A, which is to say we have a resource of A. So given a resource of A and a function that knows how to produce another resource given that A resource of type B, then we can produce a new resource, a composed resource of type B, that when used will bracket the first resource, produce the second resource, and then run our usage program. Now, of course, I'm sure that you've apprehended this. So let's see a different example. If we look just at the composed operation, and we remember that the apply function on codensity is actually bracketing, then we can substitute the bracketing in, and we get back the same nested bracketing thing that we've seen before. So when we flat map codensity values, we're actually creating values that represent this sort of nesting blocks of resource acquisition and release, which is very, very cool, because now we can actually do something with these. So the same resources value that we produced before that tuple the two resources together will now, when I use it, will execute my function and run my finalizers in reverse order of acquisition, which is very, very nice, because this is exactly what I was looking for. And now I can nicely and sanely sequence resources together in 4 comprehensions. And of course, since this is a monad, it is also an applicative. And you can also traverse structures that are traversable and acquire resources for all the elements in the structures and get back a value that will run all the finalizers in reverse. This is very great. Now, another interesting way to look at this is as sort of creating regions. So if I have a 4 comprehension on IO values, then when I bracket in a resource of type A, then that resource is only valid in this scope right there. And the B resource type is only valid in this scope right there. So of course, this is the same nesting structure that we've seen before. It's not very optimal for composition. And in contrast, when we sequence computations using our resource combinator, the codensity combinator, then we're creating regions that extend all the way down to the 4 comprehension, which is much more amenable to composition. So here, the A resource is valid all the way to the bottom, and the B resource as well, which is very cool. And this is a good way to visualize how the codensity is like pivoting the bracket operation all the way down. OK, so codensity is 18 lines of code in total. This is a surprisingly little amount of code for such a big value. And cat's effect includes resource, which is provides the same functionality. It's implemented slightly differently to accommodate streaming types as well. And Scala Z ZIO includes the managed resource. We've added it a few weeks ago. So managed is mostly the same. And in Haskell, you can use either resource T or managed by Gabriel Gonzalez. And these are mostly the same. So to summarize, I'd like to encourage you to not be afraid of the exotic data types and to always be on the lookout for examples. And I'd be happy to take any questions now. Thank you.